Okay, so thank you very much. So I'm very happy to be here because I think the first time and the only previous time I was here was 5 years ago in a seminar you organized, I think, Michael, about AI and mathematics. And at the time you presented a slide saying what could be mathematics in 2030 thanks to AI. And you know, the projects were very, very different from what we do now. So it's nice to see how much things have changed. So I work in Meta, I do AI for math, I've been doing that for about 5 years. And I'm going to talk about what I'm doing, but especially from the point of view of generated data. So the kind of research I'm doing, I'm basically considering solving problems of mathematics as a translation task, just like you would translate from French into English or from one language to another. So I want to train models to translate problems that I encode as sequences, because transformers process sequences, in some mathematical language, into their solution of the sequence in other mathematical language. So I'd like a model, for instance, to be given the sentence 7 plus 9, 3 words, and translate it into 16, 1 or 2 words, depending on whether you consider words are numbers or digits. Or provide, you know, a polynomial, x squared minus x minus 1, and translate it either into its roots or maybe into its derivative or something like that. To give an example that we're going to see again, suppose I want to train a model to learn a GCD. So I got pairs of integers and I want to compute their GCD. So I can build a huge training set, you know, of examples of that to train my model. I can represent my integers as sequences of digits in some base. So, you know, in base 10, 10 is plus 1, 0, plus 1, 32, plus 2. And I want the model to translate plus 1, 0, plus 3, 2, 10, 32 into plus 2. Just from generated examples and without doing any mathematics. For at this point, the model doesn't know what a 1, a 0, or a plus is. I could replace all those tokens by different names. It could be blue, red, yellow, blue, something, something. You know, I could change all the names. Plus could be bananas or whatever. It would work still. So that's the main idea. The funny thing is that it works. I've been doing that for a couple of years. So things we've done over the time, I'll show that we've been using that to do symbolic integration at pretty much the level of Mathematica. We've been doing the dynamical systems, so Amaury showed that a while ago. We've been doing symbolic regression, we've been doing cryptography, cryptanalysis of cryptography. I've been using it for theoretical physics and quantum computing, etc. So what does it mean, mathematics as a translation task? Basically, there's always 3 steps. You need to generate data sets, large data sets of problems and solutions to train your model, and I'm going to talk a lot about that. You need to represent your problems and solutions as sequences. I didn't intend to talk about that, but Amaury said I would, so I will. And then I need to train my transformer to translate the problem into solutions. Okay, so more specifically, I want to talk about the training data. I'm training from generated data. This allows me to have the largest possible data sets. I can generate as much as I want. But there's an impact. What is the impact of synthetic data on learning? And it's an important question, you know, for LLM in math, in physics, etc. And it sort of loops on what Julia discussed this morning. So I'm going to show first a first example, which was original paper with Guillaume Land 5 years ago. We trained transformer to do undergrad math, to compute symbolic integrals and also solving ODE. So yeah, I think you know what an integral is. So you have a function and you want to find the antiderivative of it. It's undergrad math, but don't underestimate it. It's not trivial for mathematicians. I don't think many people here could do that in their head. And it's also very hard for machine. There's an algorithm which is known as Risch algorithm, but it's extremely hard, supposed to be complete, but it's never completely implemented because it's extremely hard to actually implement technically. So you see what we want to do. We're going to encode problem as sequence of symbols, and I'm going to discuss this now. Then generate data, so generate pairs of functions and integrals to train the model, and then train the model. So how do you encode everything as sequences? So how do you treat math as a natural language? So the good news is that most mathematical objects are basically symbols and sequence. Math is full of words, you know, constants like pi, well, that's a word. Vectors, matrices, they're already sentences, if you like, they're already in sequential form. Graphs are sequences of edges, which are themselves sequences of nodes, etc., etc., etc. There are basically two issues. How do you represent numbers? And how do you represent expression, functions, equation, that kind of thing? So for numbers, integers are easy to represent. We can represent them as sequence just as we write them, you know, sequences of digits in some base. So, you know, 1024 could be plus 1024 in base 10 or plus 1024 in base 100 if you want to save space. Then once you can do integers, you can do rationals because they're just pairs of integers. And you can do reals that are symbols, you know, they're just expression. And as for real number, the way we encode them typically is just like you do them in computer science. So you need to put them into finite precision. You're in a computer, you have no choice. But you can encode them at triplet of sign, mantissa, and exponent. And then if you can do reals, you can do complex, etc., etc., etc. How do you represent expression? Well, there's a magic here. It's very easy to represent an expression as a tree. You know, computer scientists do that all the time. They call it abstract syntax tree. Logicians have been doing that since, you know, the beginning or maybe the middle of the 20th century. Curry calls those ob systems, if I remember correctly. So basically, you have a tree here, and the operators are the internal nodes, and the numbers are the leaves. So 2 plus 3 times 5 plus 2 can be represented as a left tree, you see. And the good thing is that you don't need the parentheses and all that. But if you get a little more creative and decide that you just don't want just numbers, but you want to add x, well, or add new functions like the power or the cosine, it's still the same tree. And you can get even more creative and having Greek letters to represent, in that case, to represent constant and functions. And you could have differential operators and represent here, you know, a differential equation. I don't write the equal 0, that would be at the top. There's no real need. But you see, you can represent a lot of mathematical expression as trees. And this is good news because once you have a tree, it's very easy to enumerate it into a sequence. So we use Polish notation. Basically, you start from the root, parent is enumerated before the child, and children from left to right. So here, start from the roots, it's plus, then 2, left child, right child, start from the root, 2, 3, plus 5, 2. And having done that, you can, you know, transform as sequence any function you had. So we are, in this case, totally ready for the transformer. So, yeah.
Tell us about what positional encoding you use.
So we use position, in everything I use absolute positional encoding because I don't really care about the length of a sequence. I don't have a problem of generalization to other lengths. Or to say it more precisely, when I have a problem of length of sequence, I usually have a problem of mathematical scaling of my problem, which is much more complicated. So I don't bother with anything else than absolute. So how do you generate data? So there are basically, in this case, two main methods for generating data. You remember, I'm trying to compute, I want to train model to do integration. The for-one method is the natural way. You generate a random function, small f. How do you generate a random function? You know, a function is a tree, so generate a random tree and just randomly choose operators and variables. And you compute the integral, big F, and you have a pair, small f, big F, rinse, repeat that 10 million times, and you get your training set. Of course, the problem of that is it only works if you can solve the problem, so it won't work for an open problem. And it tends to be slow, and in this case, you know, the solver we have are not perfect, so it only generates the function that the solver can solve. The other approach, which Amaury talked about this time earlier, is the backward approach. So instead of finding the solution to a problem, we try to find the problem to a solution. So we generate a random function, big F, and we compute the small f, the problem, which in this case is very easy to calculate because it's a derivative, which is, you know, very easy to do. So there are two ways, and we can try. So just to give examples of backward generation, I added this morning because there was a question about that. In this case, backward generation is very easy, but sometimes it's a little more complicated. So in this paper, we wanted to do first order ODE. So you want to generate an ODE and its solution. You would like to generate an ODE from its solution. That's a stupid method, you know. If you write y prime equals the derivative of the solution, you have an ODE that is verified. But you're not training the model to solve ODE. You're training the model to do integration and ease your problem. So the method we use here, to give you an idea of the way we do that, we can say that the solution of first order ODE are always defined up to an integration constant c. So we can always represent the solution, y, as a function of x and c. Okay, so let us generate a random function f of x and c of two variables. Suppose we can invert this by solving in C. So write it in the form big F of xy equals C. And I differentiate. I'm going to have a differential equation solved by small c. Okay? Let me show you on an example how it works. I generate a random function on the left, x log c on x, which is the solution. And I would like to find a differential equation verifying this. I'm going to solve in C. So C equal x times exponential of y on x. I'm going to differentiate and simplify. And that's the function. And you can see here, I'm making things very difficult for the machine because it's difficult to find the solution from the shape of the function. The function simplifies very nicely, and there's no way the model is going to reverse this process. With me? Okay, so let me be back at that was just an example of backward generation. So let me be back at the integration thing. So we train models which are transformers, 6 layers to, well, a relatively simple transformer with a few tens of millions of parameters. We train on generated data between 20 and 40 million examples, and we test on held out data, so on data set that were not seen at training. And then you always verify, you need a verifier, in that case SymPy. Basically you check that the derivative is correct, or in case of a differential equation, you check that the solution is, well, when you put it into the value, it simplifies to 0. So the good news of that, but that's not what I want to talk about, was that it worked. So you see on the two forward and backward data sets, we reached 93 to 98% accuracy, which meant that almost all the functions in a test set that were not seen at training could be integrated by this model. And just to compare, these are the performance of Mathematica, MATLAB, and Maple. So they are playing on our field. Basically, we generate the data to test them, so we made things harder for them and easier for us, probably. But still, we're doing at least better, at least as well as them, and probably better. Okay, so yeah.
Stephen Wolfram written to you asking if he can use this?
I don't know. I don't know if they use it. I think there are better ways to do it than this. But still, it showed that this approach, and it was surprising at the time because, you know, no one thought that this could be possible. But what I'm interested in is something else. In this evaluation, I'm integrating, so I have two training sets, the forward and the backward training set. I train on my forward training set, and I'm keeping 10,000 examples to serve as a test set. And same for the backward. So my model is tested on the same data set or data distribution as the one it was trained on, which means that everything is done in domain. I'm not changing the distribution. If we were to use that in real life, there's absolutely no reason that the test examples would come from the same distribution. So can we test that? So the way to test it is to say, okay, suppose I train on forward and test on backward, or the other way around. So here, the lines are the training data, and the columns are the test data. So you can see if you train on forward and test on forward, you start with 95% accuracy. But if you test on backward, it goes boom, you go down to 11% accuracy, which is still non-trivial at all, but it's quite disappointing. And even if you use beam search, so you have the model generate many solutions and you verify and you take the best, you're still only at 17%. It's not very good. Note that if you train on backward and test on forward, it's not symmetrical, it's much better, but it's still quite disappointing. So what's happening here? So I believe this is totally due to the way we generate, to the data we generate. So these are examples of functions and primitives generated with the forward approach. And this is what you get with the backward approach. You see, the forward approach generates small problem with long solutions, whereas the backward approach does the opposite. It generates long problem with small solutions. And this is due to the way, things simplify, or rather tend not to simplify. A random function usually doesn't simplify well. So the problem is that you have the explanation here. The thing is that when you train the model on the forward distribution, you're going to show the model, So when you train the forward on the forward distribution, you're going to show the model like 40 million of examples, and the model only has this to learn. So the model is going very quickly to learn the cardinal law of integration according to this data set, which is, it's an expansion. You have a small problem and a long solution, and the model will be certain about it because it will have seen it in every single example it trained on. So of course, if you come at test time with this example, what happens? Everything breaks. To give a trivial examples, if you train a model to recognize dogs and cats, and all the training picture of dogs are big dogs, and at test time you arrive with a Yorkshire, a very small dog, I'm ready to bet the dog is going to be classified as a cat, just because, the distribution has changed. So, fortunately, in this case, we can generate another training set by leveraging integration by part. The idea is that suppose you generate two random functions, like backward, big F, big G, you compute the derivative, and then you already have generated lots of data. So you look up inside your training set whether you already know small f times big G. If so, you know big F, small g for free, thanks to the integration by part rule. It looks like a strange idea, but when you generate tens of millions of examples, this happens a lot. So it was very slow to generate, but we could generate from the backward model an integration by part model, which has one big virtue, which is, it's much more balanced. So the problem is still a little shorter than the solutions, but they're more balanced than before. And so let's see what happens if now we do the out of distribution table, but adding in test set the integration by part data. So you see for the forward data, you train on forward, test on forward 94%, on backward 11%. But on integration by part, which is completely different from forward, you're back at 86%, which is not 93% granted, but it's a very good thing, good level. So what you see here is that there's this problem of out of distribution generalization, which means a model trained on some data set tend to generalize to data sets that are close to the training distribution it was trained on. That if you try to test it on a distribution that is far away from the training distribution, like the backward distribution in that case, things break. But out of distribution generalization still is possible when the test distribution are sort of in the middle or not too far. So we here have a first intuition about the role of training data, which is training data, OOD is the real problem in those kind of problems, mathematical problems. But it's not a hopeless cause. It's something that must be controlled and understood precisely. Okay, so I'm going to show a second paper where,
So switching them. So instead of integration by parts, why did you not just train on forward plus back? I mean, a mixture of forward.
Oh, so the mixture always works. The mixture always works because it has seen everything. The problem is how do you generate a test set that is different from both values? So integration by part was a way to balance the thing. Because if you mix, the idea many people have is, diversity is king. So you have 10 different generators and you mix them. But you're only good on the sum of the 10 generators. If you have an 11th generator as your test set, then you have the same problem. So here it's about OOD. It's about really, testing on a different distribution than a training distribution.
So you're still missing forward plus backward, tested on IPB.
Oh, that would be larger than that, or around 90%. I think it's in the paper, yeah.
What about simpler out of distribution, like just adding functions to get more complicated functions than the training?
So you can do that. That's basically what we did in the forward case. What you don't want to do is to have much longer expression than those seen at training, because then you get a problem with the positional encoding. And you get a problem that, models that have learned on short functions, no short functions and not long functions. So you have different kind of problem that's solved in a different way. Yeah.
So do you collect 100 to 200 high quality integration test examples that are kind of close to what users actually want to use? Does that exist?
So this is what I would do if I was writing this paper now. But this priming thing is an idea we got, between last year and this year. So yes, this is probably a good element a good aspect on the solution.
Another, this is unfortunately kind of a long question, but you could also imagine a system that doesn't just go straight from input to output, but given the input, produces a sequence of transformations drawn from a set which are guaranteed to work. So that would be more like theorem proving.
Yeah, it could be possible to do that. It's not absolutely sure that it would be an easier problem.
Probably not easier, but it would be.
Yeah, it would be interesting to try. Yeah, we had a bad experience with that on a same kind of dynamic system with Amaury a while ago, where basically we were doing the controllability of dynamical system, and when you calculate the controllability, you need a Jacobian to say anything. So we said it might be a good idea if instead of having just the system to predict the solution, we said system plus Jacobian predict the solution, and actually the performance were worse. The way we understood it is that the problem is that you have a trade-off. If you add a Jacobian, you have a much longer sequence of input to process, which has more information in it, but the transformer needs to understand how to use the information. And so sometimes if you need to give more information to help find the solution, you have a balance between the increased complexity of the problem you're solving versus the gain you get at the solution.
Just as another baseline, if you train it to learn differentiation, is it perfect? Or?
So this, I think we tried it and it worked at about the same level. What we couldn't prove was whether one was easier than the other from the transformer perspective. But if I were to redo that, that would be experience. So the second insight on those data generation problem is a later paper called Linear Algebra with Transformers. So the idea was say, okay, can you learn basic linear algebra? You have got a 5-5 matrix. You can tokenize all the entries with random entries. You can tokenize all the entries, as sine mantissa exponent, round them to 3 decimals or something like that. And you provide the model with matrices and solution, and you want to know whether they learn. So the good news is that it's very easy to learn to transpose a matrix, to add a matrix, to multiply 2 matrices or multiply a matrix by a vector. And what's even more amusing is that you can learn to calculate eigenvalues with pretty good precision. You can also do eigendecomposition, so calculate eigenvalues and eigenvectors. You can do SVD decomposition, but for smaller matrices, and you can do matrix inversion up to the conditioning factor of the matrix. If it's badly conditioned, it doesn't work, but it doesn't work for NumPy either. But what I was interested here is, this is possible.
What precision numbers do you use?
So typically, in order to evaluate, so I'm evaluating on a matrix, so I'm comparing the solution, the unique solution, or a reconstituted solution. For inversion, you multiply the two you compare with identity. And the way we calculate it is that we use L1 distance on the entries of the matrix. Why L1 and not L2? Because of the eigenvalues, because the high eigenvalues are much easier to learn than the easy one. And if you use L2, your metric is going to tell you that the model succeeds, whereas it has mostly only learned. And so you want the L2 matrix, the L2 error, the L1 error, relative L1 error, to be below 2% or 5% or 1%. So here most of the result up is 5% precision. Yeah. So close enough to the values. Yeah.
And when it's wrong, is it really wrong or it's just a little off?
So I don't present it here, but that's another paper. I studied this very precisely for the eigendecomposition case. So in the eigendecomposition case, what you have, because you think LLM hallucinates, so when it's wrong, it's totally wrong. So I wanted to look. So eigendecomposition, I use a large test set, and I had like 8,000 errors. And in eigendecomposition, you try to predict a diagonal matrix, which is the eigenvalues, and an orthogonal matrix. In that case, the input matrix was symmetric. So an orthogonal matrix that should have, columns and rows that are one norm, unit normed, and 2 by 2 orthogonal. And so what I noticed is that in almost all errors, the eigenvalues were correct. So the model would never, when it failed, the eigenvalues were still right. And that the orthogonal matrix that was learned would have one unit norm vectors and columns and rows, but orthogonality was not always respected. So to answer this question, in this specific case, when the model fails, it fails for a relatively good mathematical reason, and it doesn't fail too far from the correct solution. For inverse matrices, it was typical. The 10% you have here, you can predict them perfectly by looking at the condition factor of the initial matrix. If it's over a certain value, it fails, always. If it's below a certain value, it succeeds, always. So the errors in this specific case tend to be predictable.
And then a transformer works much better than an MLP with the same number of parameters?
So MLP, I couldn't make anything work with MLP. The funny thing is that this works with LSTM and GRU. So you need sequential model. You don't necessarily need transformers to do that. So what I was interested here was the importance of training distribution. And eigenvalue is a good example because we have a lot of theory. So the 5-5 symmetric matrices I'm using are generated as matrices with independent coefficient, and those are known as Wigner matrices. And because the coefficients are independent and identically distributed, I know in advance that their eigenvalues will be distributed according to a semicircle law, which is bounded, symmetrical around 0, and that the variance, the size of those will depend on the variance of the coefficient and dimension of the matrix. So the question on in-domain versus out-of-domain is, when I'm training my model on Wigner matrices and it has 100% accuracy, does it learn to the eigenvalues of symmetric matrices or just the eigenvalue of Wigner matrices? And the good thing here is that we can easily test it by changing the training distribution, either of the training and test set. Basically, you can always represent a Wigner matrices as a product of an orthogonal matrix, a diagonal component, and an orthogonal matrix, with D diagonal with entries as a semicircle and H orthogonal. So if I'm generating random orthogonal matrices, either by generating Gaussian Wigner matrices or something like that, and change the diagonal to any distribution I want, I can generate sets as large as I want of as many matrices with any kind of distribution of the eigenvalues. In other words, I can control my distribution to almost perfection. So I did that to generate 7 different distributions. So 4 distributions with positive and negative eigenvalues, like my Wigner matrices. So I have my semicircle group, which has the original Wigner matrices, eigenvalues as a semicircle, and uniform eigenvalues that would be distributed uniformly, or Laplace or Gaussian, with the same variance as the one you would get inside the Wigner matrices. And then I tried with 3 distributions with only positive eigenvalues. That would be, the absolute values of semicircle or Laplace, and the Marchenko-Pastur distribution, which is basically the distribution of covariance matrix, 5-5 covariance matrices, which is close to a statistical distribution, if you like, or a real-world distribution. And the thing is that we can then train 7 models on those and test them on all the distribution, which is what you get in this table. So as before, the lines are the training models and the columns are the test sets. So you see the first line, if you train on Wigner and test on Wigner, first line, first column, you're at 100%, told you. But as soon as you change the test distribution, things start to blow. Uniform Gaussian Laplace, you're down at 30 to 30% accuracy, which is again non-trivial, but disappointing. And if you want to predict positive matrices, positive definite matrices, then you're very close to 0. The model has seen none, it cannot learn. If you look at the free last line, if you train on positive definite matrices, the model is going to predict the eigenvalues of positive definite matrices, but it has never seen a negative eigenvalue. So it will not predict one for you, no matter how your matrix is configured. But the funny thing is the line 3 and 4, you see the Gaussian and Laplace distribution. These are weird distributions. These are distribution of matrices with a distribution of eigenvalues which is fatter than the semicircle, or has longer tails than the semicircle, and which correspond to matrices with non-independent coefficients. I don't know what they are really, but you know. The funny thing is that if you train on those, not only do they achieve 100% on their distribution, they also achieve 100% on the semicircle distribution, and they also achieve 100% on positive definite matrices, even though pretty much none of them, the probability, you know, of them having all positive eigenvalues is very, very small. This 2 to the minus 5. So you can see here that whereas out of distribution generalization is a problem on my Wigner matrices, you see it doesn't generalize out of distribution, there seem to be special distribution where generalization out of distribution happens, and not happens, but happens very far from the distribution, from random matrices to definite positive matrices, which is quite a surprise. A funny thing is that those robust distributions have even better properties in the sense that models trained on them learn faster. So here I did two things. I constrained the number of training data. I trained on only 36 million examples, which is relatively small. And I tried to do larger eigenvalues, 8, 8, 10, 10 matrices. So you see, if you train on a semicircle data, the model achieves zeros on 8, 8, and 10, 10 matrices because you don't have enough examples. You would need, with 100 million, you'd get 8, 8, but never 10, 10. But if you train on Gaussian and Laplace, not only do you get 100% on Gaussian and Laplace, but you also get 100% on Wigner. In other words, if you want to predict quickly the eigenvalues of Wigner matrices, the best training distribution is not an ensemble of Wigner matrices, but it seems to be an ensemble of Gaussian or Laplace matrices, which is extremely counterintuitive, if you like, because, you know, received wisdom is that you need to train on the distribution you test on, if you can. In this case, you can see, no, it's sometimes you can be training on distributions, you know, that are different from the distribution we want to test on, and it works. And you could also this way achieve, you know, get 10 to 10 by 10 layers, matrices, which is the kind of thing you couldn't do with Wigner trained matrices. Okay, so the takeaway here is that out of distribution generalization is possible, and it seemed to happen for special robust distribution that also allow for faster learning. So next point is, you know, how do you characterize those strange distributions?
And have you done any like interpretability of what?
So on this it's too difficult. The problem is that the calculation of eigenvalues is a complex algorithm. Transformers are difficult. The only thing I could get on interpretability here is that thing related to the L1 and L2 norm. It's very clear that the model is learning the large eigenvalue before the small ones. But in this case, for the Gaussian and Laplace, no. The problem is that I don't also have, well, I don't know.
All this work for linear regression, you know, so like the easiest way is to make a loss function that minimizes.
Yeah, you could do that, yes. Yeah, this definitely would be possible, I think. So I'd like now to present a couple of more recent results about the GCD. So Julia talked of it, and this is a result about, again, distribution, training distribution, but also interpretability. So I'm now looking for a very, very, very simple problem, which is calculating the greatest common divisor of two integers. I sample my integers between 1 and 1,000,000, so I get 10 to the 12 different problems. So the model is not going to memorize the problems and the solution, not way too many of them. I compute the GCD and I train a model to predict it. And then once the model predicts, I test the model, you know, from time to time during training on a very large held data set of 100,000 examples. So, and all operands are randomly distributed. So why do that? I had noticed, so it's known that addition is relatively easy to learn on a transformer. Multiplication, on the other hand, is a fairly hard problem to learn. And I wanted to see whether rational arithmetic worked. And my initial experiments showed that it's very easy if you give a number 4 values, A, B, C, D, that represent two fractions, A on B and C on D. The model takes no time to learn whether to compare the two fractions. Comparing the two fractions is very easy for a transformer. But I never could get a model to add 2 fractions, multiply them, or just simplify one in lowest terms. So I was saying, okay, is it because of the GCD? So that was the idea, the rationale of this study in the beginning. So you know the drill now. The idea is that you're going to generate things and you're going to encode your numbers as sequences of digits in some base. So which base? So if you have a small base, you will have long sequences that are harder to learn. If you have large base, you'll have smaller sequence, but you'll have larger vocabulary that will take more example to learn. Also, do you want a prime or a composite base? In a prime base, fractions never simplify. In a composite base, lots of fractions simplify. So I tried it with a relatively large composite base, and it seemed like I struck gold. If you try in base 30, I'm having transformer with 1 layer and 64 dimensions. That's 300,000 parameters, the smallest transformer you'll ever see. And I get, after just 300,000 examples, the model achieves 85% accuracy, which seems huge. And, if I train enough, I'm at 95% accuracy. So it seems that, it's easy to learn. Well, until you try base 31. 31 is the green curve at the bottom. And you see in base 31, same examples or same kind of example, the model goes to 61% and never goes up. So the model doesn't learn. And it gets more and more curious if you vary the base. From top to bottom, you're at 30, 6, 10, 2, 3, 31. The performance seems to depend on the base you are using for the encoding. And now, this doesn't seem logical. The GCD doesn't depend on the representation of the number. So is the model learning the math? What is the model actually learning here? So to understand that, you can look at the model prediction. And this is the whole point of 100,000 test sets that I built. So in this table, I have 100,000 test examples of random GCDs, pairs of GCDs, but I get 1,000 GCD pairs with GCD1, 1,000 pairs with GCD2, etc. And here you can see every line is the result on 1,000 pair with a GCD, and you have a percentage which so I'm giving you the most common prediction of the transformer and how often it happens. So in base 2 and base 10. So the first thing you can see is that the third and fifth column is always 100% when it's not 99 point something, which means that the model for pairs with the same GCD always make the same prediction, which again is a bit surprising, because if I give you 2 pairs, A, B, C, D, and tell you do they have the same or not the same GCD, it's quite a hard problem. But the model has no problem with that. It classifies pairs with the same GCD in the same class, and then it predicts a unique value. So in base 2, you can see in bold the correct prediction. The model correctly predicts 1, 2, 4, 8, 16, 32, the powers of 2. It goes beyond that. For base 10, you have 1, 2, 4, 5, 8, 10, 16, 20, 25, 32 as well. No, not 32. So products of, small powers of 2 and 5s. So the model knows how to predict the products of divisors of the base. But what's interesting is that there's a lot of patterns here. If you look at base 2, you can see that all the odd numbers are predicted as 1, always. All the even numbers are predicted as the largest power of 2 that divides both of them. Okay? And if you look at base 10, there's also kind of a rule appearing. In fact, by looking at this on many bases for many models, so what's happening for base 2? For base 2, what I suspect the model is doing is that it's just counting the zeros. If you look at the binary representation of an integer in base 2, the largest power of 2 that divides the integer is the number of zeros on the right. So the model has a very nice shortcut here. If the model just learns to count the rightmost zeros, and you see 28 and 14, it's going to say, oh, 2 zeros, 1 zeros, GCD must be 2. Of course, it's wrong. But that's the model prediction. Sometimes it works, 60 and 56 will work perfectly with this algorithm. So it's a wrong algorithm that works. And the same is true in composite base. You know, why in base 10 do you predict 20 or correctly? Because all the numbers that have GCD 20, the two numbers must end either with 0, 20, 40, 60, or 80. So if the model memorizes a very short list and looks at just 2 tokens, it's going to be able. So that's what the model seems to be doing. But more specifically, I could, by looking at model predictions, say that in this case, I can predict every prediction on my test set of every model in every base by applying 3 rules. So the first rule say predictions are deterministic. The model predicts a unique value, f of k, for almost all pairs of integers with the same GCD. So the GCD, if you have a GCD, everything is classified, is predicted the same. The correct prediction, which are the case where f of k equals k, are products of primes dividing b, specifically products of small powers of prime dividing b. Okay? And in the case where the model outputs an incorrect prediction, the incorrect prediction is the largest correct prediction that divides k, always. So you see in this case, the model, and this is true at all times during training. So the model, with this, I can, by looking at the results, I can perfectly interpret what the model is doing, what the model is learning, right? But it's still a bit disappointing because you see how you get good results. You get good results for base 30 because it has so many dividers. You get bad results for 31 because it has so few. And if you want to get a very good result, you can go for base 420, you know, 4 times 3 times 5 times 7. And you'll get to, you know, 97%, but you actually only learn 38 of the 100 first GCD. All those are predicted correctly, all the rest are wrong. So it's disappointing. Fortunately, you can do better if you use large base. So I tried base 2023 for, you know, timely reasons, which happens to be 7 times 17 to the square. If you train on this, what you're going to see, so these are 3 learning curves. You have the losses on the right and the number of GCD predicted on the left. The epochs, each epoch corresponds to about 300,000 examples. So 100 epoch is 30 million examples. That's a lot. So what you see is that after 10 epochs, the model learns, as predicted by the previous theory, 1, 7, and 17. It knows the divisors. And that's divisors of the base, and that's all. And then you wait, and the train loss is flat. You see the loss curve at 0.5, which is totally flat for all experiments. And then suddenly, after 100 experiments, actually the time when it happens varies from one initialization to the other. It seems to be some relatively random variable. All of a sudden, the model learns 3 more GCD. It doesn't learn 1 by 1. It learns 3 more in a very short period of time. And the GCD that are learned are 3, 21, and 51. So 3 times 7, 3 times 17. So it's like all my group of 1, 7, and 17, my predictions, are now split in 2, 1, 3, 7, 21, and 17, 51. And then after, again, 100 epoch, I'm learning 2, and then I get a couple new predictions and so on. So you can see that if you train the model for a very long period of time, the model is going to learn not only the divisors of the base, but also the small primes and their powers. And the idea is that if you let it run for enough time, eventually you're going to learn all the GCDs. But it's obviously not efficient, it's very slow. But the model seems to be able to learn, from ways I don't really understand, a full algorithm for learning GCD. But still, I only learn a few GCDs with this. So the next point is, could we do better? So you could do better by engineering the training distribution. Remember, that's what I want to talk about. So far, my training set have uniformly distributed operand, which seem like a decent idea. You know, you want numbers between 1 and 1,000,000, or sample them randomly. Problem is, if you sample them randomly, 90% of the number are larger than 100,000, which is a small GCD like GCD 69 is almost never seen during training, which is totally at odds with the way we learn and teach GCD, right? Or teach arithmetic, right? We teach small example to generalize for the large one. The model doesn't do that. And there's a way to do that, which is to increase the value over time, which is called curriculum learning. But it's known to have problem. That is, as you increase the values, the model, the values of you get to large values, the model tend to forget the small ones. But there's a way around it, which is we could engineer the training distribution. We could have log uniform operands. So instead of having numbers uniformly sample, we sample number k with a probability 1 on k, or proportional to 1 on k. And if you do that, you see the training curve. They get a bit noisy, but you still see the steps. But the models learn much faster. So when you do that, you have as many 1-digit number, as 2-digit, as 3-digit, as 4-digit. So you go to the model and you say, be my guest. I give you a lot of easy examples, memorize. And you're going to generalize. And it works. And it works. So if you do that, you can learn with that all primes up to 23. And instead of, in the past being able, for base 10, I used to be able to predict about 13 or 14 different GCD. Now I'm at 40. I'm at 48, yes. And for large base, I can know, but the model can learn up to 73 GCDs out of the first 100. So the model is clearly learning more by changing the distribution, by changing the training distribution. The test distribution doesn't change. So this is an even better example of those robust and special distribution I was talking about. But you could push that further. We talk of the training distribution, but what about the outcome distribution? As Julia mentioned, the natural distribution of the GCD, if you have random pairs, the GCD are distribution as 1 on k square, if k is a GCD. That's an old theorem by Cesaro. So it means that the large GCDs are never featured in the training set. There's 100 times less GCD10 than GCD1. So when you train the model on those kind of examples, the large GCDs are hard to learn because you see no examples. So what if you use a log uniform distribution, 1 on k instead of 1 on k square? Well, you see at this time, I go up to 91 GCD out of the first 100. So the model almost perfectly learns everything, and all GCDs up to 53 are learned this way. So again, by improving the training distribution, by biasing it, first on the distribution of input, but then the distribution of outcomes in a training set, I can significantly improve. I can turn a model that doesn't really work into a model that really works. At this point, you might say, okay, we're improving the distribution. Why not have a uniform distribution? Well, I tried, and it doesn't really work. You see the accuracy, which is the number of GCD predicted from one epoch to the other, and it's totally random. So the model still learns GCD 1 by 1 as before. The loss is flat, but there's something totally crazy happening here. If you look at the prediction in this case, I'm showing you here the predictions of the model at successive epochs. So you see 260s, 266, 267, 268. So if you look at epoch 266, you can see the correct predictions among the 21st. 1, 2, 5, 8, and 20 are correctly predicted. The next epoch, you see that 4, 8, 10, and 16 and 19 are predicted, but the others are wrong, and so on. But if you look at the values predicted, you can see at epoch 266, the ones are predicted as 1, 3, 7, 9, 11, 13, 17, 19 are predicted as 1. If you see at the next epoch, they're all predicted as 19. And the next epoch, they're all predicted at 73, and then at 7, etc. So the model is randomly predicting the GCD, but not totally randomly. There's a lot of method. What I'm noticing here is that the classes of prediction, the multiples of 1, multiples of 2, of products of the base, are still all predicted as a whole. What is broken by the uniform distribution is how the model, what the model predicts for every class. Okay? So in other words, you can see here a very good example of how engineering the training distribution can get you very good results or bad results if you make things more balanced. A certain volume of imbalance in the labels seems to be needed for the model to learn not how to classify the GCD, but how to affect the classes that it has calculated to the right values. Okay, so the main takeaway here is that you can see in this model, which I agree is a toy model, but that's the point of toy model. You can understand a lot of things from them. The predictions here are deterministic and they're explainable. They're not explainable as most of explainability people want to do, you know, by looking at the weights. They're explainable in the sense that if you look at the model prediction hard and for a long time, you can exactly know what the model will predict at all times during training, depending on the values of the inputs. Also, you can figure out what the model is learning. You know, the way the model is learning to predict is, it's not Euclid, not at all. It's a sieve. The model is learning to classify pairs AB by looking at a list of divisors it knows, of common divisors it knows, and taking the largest from them. So in the beginning, the model predicts everyone as 1, and then all of a sudden it predicts 2, and so you've got two groups, the odd number that predicted as, the odd pairs, that, well, the pairs where at least one of the terms are odds that are predicted as 1, and the pairs where both are even that are predicted as 2. And then those pairs are going to split into more and more. So it's a sieve. You basically learn the small primes one after the other. And once you have them, all the multiples of those on previous GCDs are learned. So you can easily understand that this model is a perfect model. It's a slow method. You know, Euclid is log O of log n in the size of the size of the numbers. This one is probably O(n) square or something like that. So it's not a very good model, or O(n). But it does predict the correct value. The only thing we've noticed is that the way the model predicts seems to have two steps. First, it clusters the value into groups, and then it predicts a value for those clusters. And clustering doesn't depend on the output distribution, but predicting the value depends on having an imbalanced distribution of the outcomes. Okay? And again, we've seen a case, an interesting case of a uniform form, a generally robust or a robust training distribution that can accelerate training and work on out of distribution. So yeah, so that's all I had to say. Transformers, so takeaways, yeah, the transformers can learn mathematics. I hope I've convinced you of this, at least to some point. I think it's a new field for research with application in science. You know, this is the kind of thing we want to try to solve open problem in mathematics, like we did in the Lyapunov function. But it's also interesting for AI because, you know, understanding what the transformers can do on problems of math is a good idea or a good start to trying to understand what transformers can do on every problem. And yeah, and the key point of my talk was about training distribution. So training distribution matter. Some training distribution are better than others. So when I saw the matrix, it was one exceptional case, but now I got two exceptional cases. So probably it's an area of research that would deserve more work and more interest. Thank you very much.
So maybe I missed it. How will you represent the numbers for the GCD task?
So for the GCD, they're just sequences of digits. So 10 in base 10 is 1, 0. 32 is 3, 2, plus 3, 2. I use the plus as a separator so that the model, you know, if you see 3, 2, 1, 0, it's difficult to know whether it's 32, 10 or 3, 21, 0. So that's the way it is done.
Can you comment more on the training setup in the large bases and grokking slide?
On the training set?
Training setup, like for example, whether the learning rate was fixed.
Yeah, so here in all those experiments, the learning rate is fixed. It's very low, 5 to the 10 minus 5, 5 times 10 minus 5. Usually I notice that I need lower learning rate than what you have in language models. And I need warm up, so getting the training, the learning rates up by small values, but I don't need to schedule it. Basically, a constant learning rate works. In harder problem, I usually use a scheduler, so I reduce the learning rate as learning happens, but not here. As for the model, here I think there are 4 layers, encoder decoder with 512 dimensions and 8 heads or something like that.
Do you know whether grokking behavior depends on scale?
So I don't know. I did try to scale those models, to change the size of the model, you know, on everything that fit on a volta, because I only have voltas. But so I can go from a few millions to close to a billion, a few hundred millions. And I haven't noticed significant difference in performance there. So on this experiment, I couldn't see, a good case that would say grokking depend on the, but then the problem here has very, very few parameters. The sequences are very short, etc. So even the small models are already over parameters. So I think there's enough slack even in the small models for grokking to happen.
And speaking of grokking, I believe in the original paper they observed it by iterating many times over the same data set.
Yes.
Here you call it epoch. My understanding is from working with you that it's actually you see each data point only once. Do you know if you see that same effect if you would use a smaller data set and go again and again over it?
So 2 questions. The first one, yes, this is not grokking. This is well, the behavior is similar to grokking in the sense that you have a flat loss for a very long time and all of a sudden it drops. And you have, those kind of steps. And this is fun because, the loss is the thing that the model learns from. So if it's flat, you learn from the gradient of the loss. If the loss is flat, the gradient is 0. So how does the model learn? But it's not grokking in the sense that grokking in the original paper happens after overfitting. So once the model has seen the same data and memorized them, and then it starts learning. In this case, the model never overfits. So you're right, it's not grokking. As for the low data regime...
By the way, I did not criticize you.
No, I'm not. No, I'm trying to explain. For the low data regime, well, the thing is that I never had thought of training on fewer data than, in this case, infinity or as many as I wanted, because I could. And actually, I only started exploring the low data regime when I started working with you a couple of weeks ago. So, but this is definitely on my agenda.
So if I understand correctly, this seems to be learning very opportunistically. So it just finds the first shortcut that will lead to some results which are correct for the specific problems. Will it make a difference if you do the same problems but with larger models that have also seen other higher mathematics, more abstract stuff and so on? Maybe it would lead them to find other algorithms for solving. Is that something?
So that might be possible. The thing is that on the case of the opportunistic thing, there's a way to eliminate the opportunism. You take a prime base, a large prime base, and the model has no easy divisors to learn. But it will still learn 2, 3, 4, the small primes in order. So yes, the model is opportunistic in the beginning of learning, but then as soon as grokking takes place, all models seems to be relatively equal. As for the pre-training on other tasks, it's an interesting question. I have never tried, so I don't really know. I'm sure this will help, if you train on symbolic tasks and perform other symbolic tasks. Here, no. Here, I don't think training on symbolic tasks would work because they use different symbols than the numbers. But maybe training on different arithmetic tasks like addition, multiplication, and all that might help. So yeah, this would be something definitely interesting to study. Yes.
Could you comment a little bit on your recent paper on scattering amplitudes?
Yes, I can. So this is an application to physics. So the main direction, so apart from this explainability, the main direction of my current research is trying to attack open problems. So there was Lyapunov. We are collaborating with people, Jodie Williamson from Sydney on group theory representation to try to find, elements of kernels of representations of infinite groups. And we've been working for a while with Lance Dixon and Carl Kramer on amplitude theory. So, in theoretical physics, amplitude is a complex function. The square of it is the probability of events. And scattering amplitudes are the same for collisions. So the problem of scattering amplitudes is that they're extremely difficult to calculate. The way you calculate them is by integrating Feynman style. So summing more and more complicated Feynman diagrams that have, so the easy diagram, the tree-level diagrams are relatively easy to calculate. But as you get into harder problem, you have loops, so number of loops inside the diagram, which correspond to virtual particles that get created and destroyed. And every time a virtual particle is there, you got two integration variables that happen in the calculation, which ends the amplitude, the exact calculation of the amplitudes, to include polylogarithm, which are ugly mathematical functions. And actually, it's iterated polylogarithm. So as you go from loop to loop, the things get more and more and more difficult to calculate. And this is a mess because in the standard model, you would need very high precision of that if you want to know whether, a new experiments, like in the LHC, correspond to the standard model or not. And the technique, the current computational technique, doesn't do that well. So, theoretical physicists, Lance Dixon and team, worked on something that they call bootstrap amplitude, which takes the problem the other way around, for what I understand. Basically, they say polylogarithm have so many known mathematical relations that we could use the structure of the polylogarithm to guess the look of the solution. And after black magic, well, for me it's black magic, I don't understand anything about it, they managed to represent this collision amplitudes for a problem. So it's not in the standard model, it's planar n equals 4 supersymmetric Yang-Mills, so it's a related theory. I'm told it's a good model, I don't know. But anyway, in this model for a collision of three gluons and a Higgs, they managed to calculate everything up to 8 loops. In standard model, the best you can do is 2 or 3, so that's enormous. And the way those amplitudes are represented are as homogeneous polynomials in 6 non-commutative variables. So you imagine a polynomial of 6 matrices A, B, C, D, E, F, with integer coefficients. And the degree of the polynomial is twice the value of the loop. So they calculated all these elements, and they noticed that these elements contain a lot of regularity. So the way they calculate it is that, they use a theoretical argument to transform the integration problem into a huge integer programming problem with tens of thousands of parameters. So that's PhD sweat. I mean, they work, it's a lot of work. But they noticed that those coefficients seem to follow patterns. So we tried to train transformer to see if they could do what the physicists had done with their PhDs and postdocs and predict, you give them half the amplitude and they predict the rest. And it turns out that a transformer can be trained to predict, well, first, whether a coefficient is 0 or not 0. Most coefficients are zeros in this. Second, predict the values of the coefficient. And even find the coefficient from the next loop from the previous one as a relation of the previous one. So we recently had a paper on that describing this. So at this point, it's only a proof of concept. Basically, we show that on data we already have, we show that the transformer can do something that is better than what human knows. And we notice a number of regularities inside, what the transformer learns that seem to hint at symmetries that, physicists don't know, which might hint at, new properties, and at least in equal for Yang-Mills. So this is the status of this paper at this point. I think it's a proof of concept that you can use a transformer to show that there are unknown relations. The next part, and the difficult one, will be to try to see how we can elucidate what the transformer is doing. Transformer obviously is learning something relatively easy to predict. We don't know what it is. So could we do symbolic regression? Could we try to do interpretability on the transformer? We don't know this yet.
Okay, let's thank Francois.